I'm going to implement an expression framework. The use case for this is that we have some system where some external user wants to configure an expression, perhaps because some part of a calculation needs to be configurable. So say, for instance, that a user wants to add a calculation to a system. For instance, we need to add 3 plus a divided by 5. This would typically be in the context of some rule-based system where we're allowed to, as a user, configure up some behavior of the system that is math-based. So what kind of object structure can we create to solve such a problem? I'll minimize the context and put it up in the corner for you. And let's write down an example so we can see it. Let's say we have 3 plus a divided by 16. So what are the objects in such an example? I would argue that pretty much everything that has a symbol is an object here. The plus, the 3, the divide, 16, and a being some kind of variable. When we draw this graph, we will start at the root, which will be the divide, and then on its left side it has a plus, on its right side 16, and the plus has on its left side the number 3, and on its right side the variable a. If we looked for the class that each one of these objects would have to be a member of, we could start with the a, which has to be a variable. The number 3 is an example of a constant. The plus is an example of an operator capable of adding its left side and right side, in this case 3 and a. I'll simply call the class adder. I'll call the root object a divider. Now this is a complete object graph that represents the expression that we want user configurable on the left-hand side. Now we can clearly see the composite structure here. The expression forms a graph. What would this look like in a class diagram? I'll minimize this drawing so we have space for a class diagram. You probably remember from the theory section that we had these 3 classes or types. The component, which is the base class, the composite that contained other components, and then the leaf, which was the atomic component. The question now is, how does that relate to the structure that we saw with the expression? Well, I'm going to replace the name component with expression. When we go ahead and implement this, this will most likely become an interface in Java. The leaf will become an atomic expression, and we've seen 2 examples of such. Constants and variables always formed leaves in the tree structure that we saw. In other words, constants and variables do not have children. The composite, however, is a little more tricky. We actually saw several composites, the divider, the adder, and we will probably have a subtractor and a multiplier also. I'm going to create a common base class for these, and I'm going to call them binary expressions. The binary expressions have a very special implementation of the composite association between the composite and component. They have a left side and a right side. It's not an arbitrary number of children. They always have one left child and one right child. So we need to replace the association. And we see a couple of examples of the left association in the picture on the left. And we also see a couple of examples of the right association. I assume the binary expression will become an abstract base class. So we also need to add the concrete subclasses of the binary expression. We would need something like the adder, probably a subtractor, the divider, and so on. As you can see, the class diagram looks quite different than what we had perhaps expected. It looks different from the composite, but the composite structure is still there. You can clearly see how we're building up a recursive structure using the binary expression. Now for something a little more exciting, let's move the class diagram to the side so we can get some space again. I'll redraw a similar structure to the one we drew before, with the divisor on top. On this left side, it has a plus with 3, and then say a variable a, and then on its right side, a constant 5. And let's take a look at how we would calculate the value of the expression at runtime. Now the trick here would be to ask the root object what its value is. Of course, a divisor cannot determine that value without first figuring out its left side. So the divisor asks the plus what its value is. Now importantly, the divisor doesn't necessarily know what's on its left side, it just knows that it can ask for its value since it is an expression. The plus will ask its left side and get the value 3. The plus then asks its right side and get the value of a, and now it can return the value to the divisor, And the divisor now can resolve its right side by going to the constant 5. Now let's say for instance that the value of a is 10, then we will get 3 from the constant and 10 from a. We need to add those together. We're going to return 13. The divisor now resolves its right side, get 5, and returns the result being 13 divided by 5. Now this kind of recursive call through the object structure or delegation through the object structure makes the composite an extremely powerful pattern, one that we use very frequently and one that you'll see be very powerful as we apply it in different situations.